Newton's law of gravity, or his gravitational equation, now allows us to relate the properties of our planet to the acceleration that it causes on falling objects. It also allows us to find things out about our planet. So here we have an object that is falling close to the surface of the Earth. Since it's close to the surface of the Earth and its center of mass distance from its edge is so small compared to the radius of the Earth, we often just approximate the distance between the centers of the masses to be just the radius of the Earth. And we can now say that the force of gravity acting on this object, the net force, would equal its mass times acceleration, which would just simply be the force of gravity. So, negative g m planet times m object over the radius of the planet squared must equal mass of the object times the acceleration of gravity that the object is falling at. Please notice the mass of the object does in fact cancel out. And I do have an equation here that I can now use to find my acceleration due to gravity if I knew the mass of the planet and the radius of the planet. However, we don't really need that for the planet Earth, since we've been able to measure by experimentation that the acceleration of gravity on the planet Earth is negative 9.8 meters per second squared, because that goes against the radius of the Earth. The radius of the Earth is going outward, gravity is pulling inward, thus it should be negative. But if we know AG and we know the radius of the planet, we can now use this equation to calculate the mass. And this is exactly how we found the mass of the planet. Not by actually weighing the Earth itself, but rather by seeing how the Earth accelerated other objects. This would be impossible to do if not for the work of Newton deriving his equation, as well as the work of Cavendish, whose work allowed us to figure out what this gravitational constant is to make the equation work. Now, using this equation for gravitational acceleration, we can predict what the acceleration of gravity would be on other celestial objects, such as the Moon, Saturn, Pluto, or any other planet. All we need to know is the radius of that moon or planet and its mass. Now, finding the radiuses are fairly straightforward and simple because we can see the moon and the planets. However, finding their masses is another story. So we're now going to figure out how we can find the mass of a planet. And to do this, we're going to just basically apply the same kind of logical steps that Newton had originally used in deriving his gravitational force equation. First, for me to find your mass gravitationally, I need an object to be orbiting you or falling towards you so I can figure out how much force you're exerting on an object. Basically, I can't tell you how strong something is unless I see it affecting something else. So, the first thing is we need to make sure that there is a moon orbiting a planet. So now we can now say that the net force on that moon is equal to that moon's mass times that moon's acceleration, just using Newton's second law. We're going to have to say that that net force on the moon is pretty much essentially just the force of gravity on the moon from the planet. Again, because all the other forces of gravity are so small, they're not going to really be of anything of important consequence. And so the force of gravity on the moon, the force of gravity pulling the moon towards the Earth, must equal the mass of the moon times the acceleration caused by gravity from that planet. And since the moon is in orbit around the planet, it's moving in a circle, which means the acceleration caused by gravity is in fact centripetal acceleration. And we have two equations we can use to work with it. And that would be either v squared over r or omega squared times r, whichever one is easiest for us to work with. But right now we have the force of gravity on the moon, and that is actually equal to g m of the planet times m of the moon all over the orbital radius squared. The orbital radius would be measured from the center of the planet to the center of the moon. Please notice that in this equation, I do have two like terms. I have the mass of the moon on each side of the equation, which means they will in fact cancel out. This reduces the equation to gm planet over r squared equaling the centripetal acceleration. And centripetal acceleration does have the equation tangential speed squared over radius. So I can just substitute that equation in for AC, and I can now come up with an equation that looks like this. Now this is a little bit of a mess, but again, I have a common multiple. I got r squared on the bottom and r on the bottom on the other side. This reduces down slightly. I can also now manipulate this equation to find the mass of the planet. So we can now see that the mass of the planet can be found by the orbiting tangential speed of the moon going around that planet squared times the orbital radius divided by the gravitational constant. Please notice I do not actually need to know the mass of the moon to find the mass of the planet that the moon is orbiting. And that's simply because the orbiting moon is a falling object, which means the acceleration is free fall, and all objects have the same free fall acceleration regardless of their mass when they're falling towards a planet. The only mass that actually matters is the mass of the planet itself causing the free fall acceleration, not the mass of the objects experiencing the free fall.